think if I hit that one. We're good. Okay, excellent. Well, it's nice to see everybody. Welcome to whatever course number this is, 68410, which used to be 6838. The numbers all changed on us in the department this semester, and all the faculty are confused. So if I say 6838 in your head, you can translate to 68410. And I've written myself a reminder on the board. It's nice to see everybody's smiling faces. I hate this classroom, so we're going to try and switch because I can't really use the screen and prove a theorem on the board at the same time. So either I'll be running laps in this room or we'll find somewhere else. So stay tuned, check your email. There's some chance, I hope, we can find another space. But for now, today, we're having the high-level, friendly introduction to the research field today. So it'll be perfectly fine for today's lecture. And then on Thursday, I scare you all out of this class and we do lots of integrals. So in any event, it's nice to see everybody here. This is a graduate course in geometry, and we introduce all kinds of fun ideas in essentially how do you input a shape on a computer, the many sources of geometry that show up in applications, everything from low-dimensional shapes to like high-dimensional things you might encounter in machine learning and data analysis, to understanding these objects, processing them, and possibly producing new ones. This is a whole semester-long thing, and essentially we spend half our time introducing you to some theory like differential geometry and related fields, and the other half of our time talking about how we can make that theory work in a computational system. As usual, we're going to spend the first 10 minutes of class today getting all of the boring, uninteresting things out of the way that we need to for the beginning of a class here at MIT, and then we'll talk, not technical, but at least a little bit of introduction. So with that, I'm going to pull up on the screen the web page for this course and tell you a bit about the logistics, everybody's favorite part of the discussion here. So in case you have not found the website for this course, that's understandable because I'm disorganized and didn't do it until last night. But there are many ways to find it. You can either go to my research group webpage and it's kind of linked from there, or if you open the course thing on Canvas, you'll find it linked right on the top there. So essentially the way that 68410 is going to work is pretty straightforward. Actually, all of the course materials will be publicly visible on this webpage. This includes the course schedule, all of your homeworks, course notes, slides, fun other stuff that I might post. All of that is going to be on this website here. If you'd like to turn in homework, which I strongly encourage you to do, then you'll do that on Canvas. And other than that, it's a very straightforward course. There's also a Piazza website that you can use for Q&A and discussion and so on. So let's scroll down the course information page real quick, just because I know if I don't say it out loud to all of you, you'll complain mid-semester that there was nowhere to be found. Right, so let's see. This class is Tuesdays and Thursdays, 2:30 to 4. Currently, we have 2 staff members. If we exceed whatever the student-faculty ratio is for this class, I'll try to get a second TA, but we'll see how it goes. So I am Justin. Hopefully you're in the right class. Again, this is geometry. And our TA is Thea. She took the class, gosh, 4 years ago? Is that right? Yeah, and had a fantastic course project. It's the only time I've ever, for one, it got published, and further, it was built into a audio controller, which was not a thing I expected at a geometry class, and super cool. But in any event, both Thea and I have office hours will be available on Piazza, all that stuff, because we want you to succeed in 6838 or whatever number this class is. Right, so essentially my office hours are going to be Wednesdays, 10 to 12. I'm in the Stata Center. Thea's office hours will be after class, so I guess 4 to 5, Tuesdays and Thursdays. Location hopefully will be the same as the classroom, but the department has not confirmed that yet. Any questions about the basics here? I know this is the really fun part. Cool. Let's go through a few details about your deliverables in this class. So here's my life philosophy. There are very few geometry emergencies. I see no reason to give you guys a weird exam where you're held under duress and asked to compute a curvature tensor. So instead of that, most of the work in this course is based on stuff that you'll do at home and on your own time. So essentially, the majority of your grade is based on 5 homework assignments. These are 50% of your grade. So you can guess how much of your grade each assignment is worth. And essentially, each one of these will be on a roughly once every 2-week basis. The first one will be posted later today. It's already written. We're just proofreading it a little bit. And beyond that, there are a few other deliverables in this class. We have a weekly engagement activity. This week will be an off week, and then starting next week, we'll have these things. And it's a sort of choose your own adventure scenario here. So we've given you a lot of different options for what you can do. You can either chat a little bit on Piazza, you can answer somebody else's question on Piazza, see what your lazy instructor did there. You can do a reading assignment. So we're gonna post like suggested research papers that you can take a look at, and then you just turn in a paragraph kind of telling us a little bit about what you learned. Or if you make an appointment with the EECS Communication Lab, that will count for your weekly thing, because a big part of this course is going to be an open-ended course project where essentially we're going to kind of simulate writing a conference or workshop paper by the end of the class. And I don't like reading your last-minute garbage writing stuff. So anything I can do to incentivize you to write early, get feedback, edit your text, and so on is important to me. So if you want to get out of your weekly thing, that's one way to do it. This class has no final exam, but the other big piece of this course, which has instructions linked somewhere. I'm sorry, I forgot where. Oh, somewhere on this webpage. Ah, here. The final project instructions are already posted on the webpage. You can do it tonight and get it out of the way. You'll laugh, but there's usually one. Right, so this is an extremely open-ended course project. This is a graduate level course. All of you come with different backgrounds and interests, and you're looking to take the contents of this course and translate it to all kinds of cool domains. That's one of the fun things about teaching this class. So the way that this project is structured, I'll let you read the instructions carefully. Essentially, there's a lot of different check-ins. Like you write a proposal, you do a check-in, you do a draft of your paper, and then a final research paper and a presentation at the end of the semester. All the details about precisely how many pages and words and space and all the things that you guys usually ask are in this document. It's battle tested over many years, so I'm sure most of your questions will be answered there. For those of you who took my undergraduate class, or my and Mina's undergraduate class last semester, so this is 6837 and or 64400, depending on what semester, should be aware that the project instructions are not the same. In particular, in our undergrad class here, your goal is to implement something from past literature. In this project, this is a graduate level course, you're expected to do something new. It doesn't need to be like I'm not going to give you a Fields Medal at the end of the semester or whatever, but we do expect, like, at the very least, like, compare and contrast two research papers, or do a cool extension that hasn't been done before, something like that. And the good news is we have ample time to help you guys discover whatever you're excited to do. Moreover, there is high probability that many of you will submit either project proposals or check-ins, and I will read them personally and say, well, that's not a good idea. And that's actually fine. So if you then, for the next check-in, you can just do a different topic if you wish. I think I've covered all of the main logistical stuff. Are there any questions before we start talking about geometry processing? It's so quiet. You know, they told me in teacher school I have to, like, ask a question of you guys and then, like, count to 10 in my mind and make it real weird for everybody, or you won't speak up. Okay, fantastic. So, right, oh, and one or two other things on the webpage here. There's also PDFs of the slides. There is a half-written book by your instructor, which will be posted kind of chapter by chapter, because in principle, I'll be trying to keep ahead of you guys. Probably in practice, somewhere midway through the semester, I'll get stressed out by a deadline and fall behind. But at least for the first half of this course, there's a lot of written material there. You can see the first two chapters, one that's just a broad introduction, and one that's reminding you of how to do algebra are already up on the webpage. There's also a useful formula sheet. I'm going to open this up really quick. So, the prerequisites for this course. Your file could not, oh yeah, my laptop won't connect to the internet today. That's okay, I have it downloaded, I think. That's frustrating. Sorry, give me like 30 minutes to awkwardly shuffle around on my laptop. Pull up God knows what embarrassing material here. Downloads. All right, well, that's not gonna happen. Okay, no problem. There is a PDF on the webpage, which you all can open. Many of you have laptops, and I'm guessing have already opened, that have useful formulas for this course. The prerequisites for this course are linear algebra and multivariable calculus, and some coding. It turns out that actually the third one is probably the loosest. The first two are the ones that you're really gonna need. So when I say linear algebra, I don't mean like, you took it 7 years ago in undergrad, you don't really remember it, and you're just kind of like happily bouncing through. Like, we are going to be doing math with equations, and it's going to move a little bit quickly. So there's a review chapter on the web page, and there's a formula sheet there, and you should look at those very closely. If you're excited for this course, but you lack the background to understand a little bit of that, that's okay, but do come to office hours and be proactive about it so that when we're in the middle of lecture, you're not just like lost and floating off in a sea of derivatives, okay? In particular, I think the main thing that oftentimes people forget from calculus class that we use a lot in this course it comes by many names. Integration by parts, Stokes' theorem, Green's theorem. Somebody else give me another name for the same thing. Divergence theorem. What was that? Gauss's theorem, probably. I don't know. Yeah, Gauss-Bonnet is not that, actually. Sorry. Essentially, all these different versions where you have an integral over a thing, and then that's equal to a boundary integral minus another thing. There are like 100 different versions of the same theory. That is a thing that comes up a lot in this course, and is something you probably haven't seen a whole lot in other parts of computer science, at least. So it's a thing to brush up on if you've forgotten. And I'll also try to remind you a little bit. Okay, I promise I'm done with all the administrative stuff. Any questions for me so far? Is this classroom really hot, or am I just dying? Okay, it's that. Cool. All right, well, with that, welcome back to 68410. My name is Justin. I'm your instructor for this course, in case you missed it. It turns out that this course is basically covering roughly what my research group works on. So I encourage you to kind of check out our webpage. And the good news is that we have a whole lab full of people in CSAIL who don't know it yet, but have basically volunteered to help you with your final projects. And they're all experts in this topic area and have a lot of cool suggestions for different directions that you can look into. In terms of prerequisites for this course, just one final reminder, we will have coding assignments. They tend to be small and self-contained. I think at the end of the day, we actually settled mostly on Julia or MATLAB assignments. I know you guys are gonna like that, but that's okay, because I'm a lazy instructor and you're grown-ups and you can figure it out. Most of the coding in this class is relatively straightforward, in the sense that the main challenge in geometry is oftentimes working out really carefully the details of some algorithm or model or equation, and then it's just a matter of typing it in the right way and then being like impressed with the cool pictures that come out. So I wouldn't let that scare you away if you're not familiar with these programming languages. I guarantee you'll pick it up pretty quickly. We need fluency in linear algebra and multivariable calculus. And I've put a list of other topic areas that are useful but not strictly required. So if these are like, I would think of this more as different kind of applications and things adjacent to this research field that might kind of support your project and help you kind of pick out some things you're interested in. And here's my philosophy. In case you haven't noticed already, I'm a pretty enthusiastic guy. I really like this research area. It's fun. This is a cool emerging field in computation, and it's very different from most of the things that you encounter in EECS at MIT. So I want you to take this class. This is fun stuff. You also have an instructor who loves this area and has been immersed in it for the last 20 years, meaning that I'm likely to write homeworks that are way too hard for you, because they're not that hard for me. And that's not on you. So if that happens, you need to reach out and you know, get help during office hours. We're very generous with this kind of stuff. And we really want you to kind of take away all the cool intuition and thoughts from Geometry World. Okay, so what does this class actually cover? Now, there are a lot of different ways to kind of think about all the applications of geometry in computer science, and there are so many. I mean, this is not the only geometry class in this department, right? We have people that do computational geometry from an algorithms perspective, or like geometry of data, and so on. The way that I see the perspective in this course is that roughly you can kind of understand geometric data in two different ways, right? On the one hand, we really do encounter like shapes all around us. You look around this classroom, you see tables and chairs and other humans and all kinds of weirdly curved objects that computers need to analyze. And there's so many different applications out there, from autonomous driving and computer vision to 3D animation, that really boil down to processing, understanding, and generating shape. On the other hand, we see this other emerging subfield in like statistics and machine learning that involve analyzing a data set from a geometric perspective, right? And so for instance, we'll see things like Laplacians and rigidity and distances and so on pop up, not just when we're discussing like cute, Stanford bunnies embedded in 3D, but also high-dimensional data sets, and the machinery mathematically is going to be very similar. And so the kind of high-level approach in this course, which sometimes succeeds and sometimes fails, is to try and present these two perspectives a little bit in parallel, right? That we're going to look at the underlying theory of differential geometry, probability, some other areas, and then show how it can apply to all these different low and high dimensional contexts, right? One of the really fun things to do is to see all the final projects that come out of this course. I mean, just looking out into this classroom, I recognize graduate students in machine learning, in computer graphics, in computer vision, and all of you guys take very different things out of a course like this, which is very fun to watch. And hard for you to structure, but that's okay. So in today's lecture, essentially, we'll probably end early. Our goal is just to give you a bit of a high-level picture of sort of one of the, what is this area all about? What are some of the tools that we're going to cover, and what are the applications that we have in mind? And so today's kind of the overview, and then starting next lecture, we're going to take a very classical geometry-style approach to entering into this field by talking about curves in the plane, which are already enough of a case study to understand a lot of the challenges that come up with making geometry work on a computer. Okay, so let's get started. Essentially, I'll tell you a little bit about this sort of applied geometry toolkit, the way that I see it in 2023 here, and some of the pieces that go into carrying out interesting work in this particular domain. So first, let's talk a little bit about the theory that underlies a lot of the work that we do in 68410. And some of the theoretical ideas in this course, of course, don't just date back to like, 50 years ago or, Turing plus, but really go back many hundreds of years before that. Probably, if I asked all of you to name the most famous geometry textbook, it's just out of curiosity, what would we guess? Do Carmo, interesting. Yeah, that's a very modern answer. Sorry, I heard another one. Euclid, yeah. So probably, I think many of us would agree, apparently not everybody, that the geometry experts may have a different opinion, but probably the best known one, if you just took high school geometry class, would be Euclid's Elements. And really, geometry was one of the earliest areas of mathematics to be formalized and studied. And a lot of the constructions in this course go all the way back to like the BC times. Now, of course, if you page through Euclid's Elements, and I encourage you to, it's frustratingly poorly written, which makes sense because he was the first guy to write a lot of this stuff down. One thing you notice is that, of course, the geometry that Euclid was worried about was a very ideal picture of the universe, right? Like, here are versions of Euclid's Elements in a bunch of different languages. It's been translated to, English, Arabic, Latin, whatever. But if we look just at the pictures, this is something we usually do in geometry. We just skip over all the text. What do you notice? I mean, all the shapes here are like circles and polygons. And so this is kind of where, your high school geometry class ends and where modern geometry starts, right? That, of course, the machinery that you developed in high school is already interesting and extremely non-trivial, right? Like, what can you construct with a straight edge and a compass and so on are really deep questions and hard things to wrap your head around. But they also don't really help you understand this LiDAR scan without a heck of a lot more machinery, both mathematically and algorithmically, right? And so bridging that gap from one side to the other is remarkably easy in some sense. It turns out like Euclid was onto something, but is going to require a few lectures in this course, to be clear. And then, of course, the modern perspective is not just to study like shapes that are embedded that we're used to looking at, but also to apply the same theory to high-dimensional data, right? So for instance, here we see the world's most overstudied data set. This is a set of handwritten digits. And one thing that's very well known about these digits is even though they're embedded in a very high-dimensional space, right? Like the space of images is like roughly the dimension is the size of the number of pixels in this image here. That there's a very low-dimensional structure which kind of governs, the different ways that people write these digits down. There have been millions of different papers out there that find this structure in different ways. So because of all these different motivations, we had to move a little bit beyond Euclid and propose different theories and ideas for how can I understand a shape both locally and globally. And there's all kinds of beautiful theory out there. You can go to our friends in the math department and learn about it for an entire PhD worth of coursework. But essentially, I think the starting point for a lot of it, at least from our perspective in this class, is the field of differential geometry. We haven't quite gotten to Anna's favorite textbook yet, but we're close. This is my favorite differential geometry textbook, not because it's well written, but just because the covers are really cute. Essentially, differential geometry is this theory that tries to take the machinery that you all learned in calculus class and transfer it to understanding shapes, right? And differential geometry is a very different type of math than what you're used to doing in your high school geometry class, right? And it's no longer just straight lines and angles, but we're trying to understand what it means to be a curved shape that's sitting inside of a larger domain, right? Like a potato chip embedded in 3D. We're going to spend a lot of time on potato chips in this class. And so in fact, if you walk over to the library and pick up this textbook series, each one of these images is the cover of one of 5 different textbooks in Spivak's Comprehensive Introduction to Differential Geometry. It tells a cute story. It ends with, I think it's like Gauss and Binet getting married or something, which is strangely progressive for the 1970s when this book came out. But in any event, you know, the theory here is deep and very challenging. In this class, we're not going to get anywhere close to the big theorems in differential geometry. We will state some of them and give you the machinery you need to understand how they're written down. But of course, the proofs are something that would take many semesters to cover in a very careful fashion. This is my excuse for not covering it. The reality is that I also don't remember how to prove half these terms. So in differential geometry, the main object of study is an object called a smooth manifold. How many of us have heard of a smooth manifold before? How many of us have seen manifold in machine learning? Math class, graphics. Yeah, it's fun. I think I managed to cover almost everybody here. Yeah, so a manifold is sort of this generic notion in geometry that generalizes the idea of what it means to be a surface, right? So a manifold is an object that is sort of intrinsically k-dimensional and possibly embedded in some higher dimensional space. So what do I mean by that? So like if we take a look at this image here, right, this funny looking potato chip, in some sense is a two-dimensional object, right? Like if I'm an ant walking across the surface, I have sort of a two-dimensional world to walk around in, but at the same time, it's embedded in 3D. Now it turns out that embedding part is going to be a little less important for a lot of parts of math, but certainly the fact that this is intrinsically two-dimensional is going to be really critical. But at the same time, if I'm an ant walking around on this surface, I'll very quickly notice that life on this hyperbolic object is very different than life like walking around on the floor of this classroom, right? So for example, if I've got my ant best friend here, and we start walking along in parallel holding hands, it's okay for ants because they have 6 legs. They can spare one. What do you think happens as they move in parallel along the surface? This picture is kind of suggesting what's going on. Well, eventually they won't be able to hold hands anymore, right? They kind of move apart. And it's that notion that starts to motivate how we can compute things like curvature, right? That this space is somehow fundamentally different. It's bent than just the flat space that we're used to thinking about from like calculus and algebra. Okay, so we're going to dive all the way into that theory as your instructor continues to contemplate whether ants have hands. So, right, if we want to formalize the definition of a manifold, which we're going to do in the coming couple lectures, essentially what we're going to do, at least informally, is to talk about it as an object that kind of locally looks like the image of RK. Right? So here we've got this shape. This is called a double torus. Any guess why? Because it's like 2 tori. Right, and so globally this shape does not look like a plane, right? I can't like, without cutting this thing, I can't just map it onto the floor here, right? I'd have to like tear this thing apart. But locally, if I take any point on the surface, I can draw a little neighborhood around that point, and there exists some function from the k-dimensional plane, in this case k is equal to 2, onto this thing that parametrizes just that little tiny patch. And this is where geometry and calculus start to meet up with each other. Because it could be that that function is non-unique, right? It could be that, like, you know, there's some other function that like maybe parameterizes it more vertically and less horizontally or something like that. And from the perspective of geometry, that's irrelevant, right? A manifold is a set of points. It is not this set of charts that map into this surface. And that's where, you know, machinery from calculus can get to be a little bit misleading. So for example, when we work with derivatives of this function phi, we're going to be very careful that whatever calculation we do is invariant to our choice of phi. It only cares about the green shape, not the particular map that we chose into this object. Right? And so it's that kind of reasoning, and I see a few kind of eyebrows raised, and that's good because this is a hard thing to think about, that we're going to be really drilling in this course quite a bit. That like a shape is a set of points. It is not like a function or some other object. Okay? So once we dig into differential geometry, we define manifold, we understand what it means to be embedded, then our goal is really to talk about how do we analyze the shape of this weird bent up object, right? Like this thing is clearly very different than the shape of just like the flat blackboard that it's sitting on. And there's many different notions that we can use to do that kind of analysis. So for example, in this course, in a couple weeks, we're going to derive two different notions of curvature. Right? So curvature is a measure of how much an object is bent. Right? So for example, if I have a sphere that is a positively curved object in the Gaussian sense, and if I have a potato chip, it's negatively curved. For surfaces embedded in 3D, we're actually going to have two notions of curvature. One is the one I just mentioned, and then we'll have a second one called mean curvature, which is a little harder to think about. And we're going to see that some of these notions actually generalize to higher dimensional objects as well. Right? So for example, if you're in relativity, you're a physicist, they talk a lot about curvature and space-time and all that crazy stuff. We're not going to dive into that, mostly because I never understood it. But exactly these same notions that we'll talk about in low dimensions lift to higher dimensional universe as well. And the really beautiful thing is that this theory tries to kind of establish, remember the title of this course is Shape Analysis. One thing I can do, I've got this 3D shape here. I analyzed it. I told you where it's positively curved and negatively curved. A question that you can ask mathematically is like, is that it? Like, is there other information that I'm missing? Like, are there two shapes that look different but have the same curvature? How many vote yes? How many vote no? How many of us are like, I'm totally lost. I don't know what Justin's talking about. I thought this was compilers. Yeah. Right. So yeah. So it turns out that, for example, Gauss proved a certain kind of rigidity theorems that say that basically if you have Gaussian and mean curvature, you have completely characterized the surface up to a rigid motion. Right? Does anybody know the name of this theorem? It's got a Latin name. You did a better job pronouncing it than I did. Egregium. Egregium? I don't know, any Latin students here? I think in Latin it roughly translates to totally awesome theorem, apparently, which is kind of cool. I thought that was cute. Like, I always assumed it was a geometry term, and it's not. Okay. So curvature is going to be a very local notion of shape, right? It tells you, right, standing at this point, like, is it bending down? Is it a potato chip? What is this thing? We also are going to look at global geometry. And the simplest example of global geometry is computing distance between 2 points. So in particular, if I've got this cute bunny here, rendered by my colleague Keenan at CMU, if I choose 2 points on this surface, I can ask what is the length of the shortest path from one point to the other, constrained to move along the surface. And that problem is known as the geodesic distance problem, and we're going to cover many different algorithms for computing geodesic distances. Those of you who are computer science students will be very familiar with most of the algorithms we cover because they look an awful lot like Dijkstra's algorithm on graphs. It turns out that a very small extension of that called fast marching is actually basically, I don't want to say state of the art, but one of the dominant tools for computing such a thing. But we'll also see that distances get really weird on curved shapes. In particular, this bunny is a fantastic example. If I start computing a shortest path on this bunny, like I just point my toes in a direction, I start walking in an efficient fashion. I'm not turning my steering wheel. Eventually, along this surface, I could end up back where I started, right? And that's not a thing that can happen on the plane. And so what that means is that there are a lot of notions of distance that we think of as equivalent from like undergrad math that we're going to find become different from one another in graduate level math. So for example, one thing we think about a lot in distance is that we could either start at a point and just start moving along a straight line, and the whole line that I've traced out behind me is always the shortest path. That is no longer the case on a curved object, because eventually a path could double back on itself, right? In which case, the shortest path is now like snapped to some other object, right? So like the notion of locally shortest path versus globally are actually two separate things when you're in a curved domain. We'll talk quite a bit about that. Moving forward in this course, we'll also talk about vector fields and flows. So one of the main tools that people use in differential geometry for understanding surfaces and manifolds is constructing basically putting hair on them. This is a sore topic for your instructor, but essentially by understanding where you can comb hair on a surface, where the singular points end up, how many of them there are, and how they circulate, actually can tell you quite a bit about geometry, and also has a number of applications, everything from analyzing weather patterns on the Earth, right? For instance, there's a theorem that says at any given time on the Earth, there's one point that has no wind, right? Because it has to circulate about something. To literally putting hair on surfaces for computer graphics application, make use of these kinds of machinery. The next big chunk of this course is going to cover one matrix that we really care about in geometry. And this thing is called the Laplacian. How many of us have encountered Laplace operators before? Now we're going to start separating out the grad students from the undergrad. Yeah, which is OK, because we're going to cover it in this course. So, in about the 1950s and 60s, there was a really famous geometry problem that people started to study, first in low-dimensional geometry and then in high-dimensional geometry. It's a really awkwardly phrased question that mathematicians asked. It's called, can you hear the shape of a drum? Now, this was a famous, famous title of a research paper. I forget exactly the year, but like, I think it was within my parents' lifetime, which is kind of cool. And they asked the following question. So let's say that I have a drum, and it's a weird shaped drum. I draw some weird polygon in the plane, and I cover it with drum material, something elastic, and I hit it, I make a sound. Now, I'm going to play a game where all of you guys turn around, you look at the other wall, I hit my drum, you hear the sound that it makes, but you didn't see the drum. And then the question I ask you is, what's the shape of the drum? Up? Oh, good. I finally connected to the internet. That's great. I accept the terms of service. No. OK. Right. So that's weirdly disruptive. OK. So we do this experiment. You hear the drum, but you didn't see it. And now the question is, could you reconstruct the shape of the drum? And it's funny, like a lot of mathematical questions have like a really clear answer, and then it still takes mathematicians like 200 years to figure it out. But like, this one doesn't. and like, if you think about this problem more and more, you can vacillate. So for example, I play the cello, and one thing you might know about string instrument is that like you press your finger down on the string while you're playing, and that changes the pitch, right? The string gets shorter, and the pitch that your instrument is playing changes. If you think about it, that's a link between audio signal and geometry, right? You shorten the length, and the wavelength that you observe, changed. So, and in fact, you can show, like, the wave equation really does work this way, right? The dominant frequency changes. So maybe there is a link between geometry and kind of spectral analysis. On the other hand, I'm giving you like a one-dimensional list of numbers, like vibration frequency of a drum, and reconstructing a two-dimensional shape sounds ridiculous. And so there was a lot of debate about this. Spoiler alert, it turns out you cannot hear the shape of a drum. There exist shapes that are what we call isospectral. Here's an example. These are graphs, but it turns out we can do graphs and shapes similarly. In fact, I think it was at Dartmouth, like there was this whole little math department dedicated to coming up with clever ways to construct isospectral stuff. But that little experiment turns out to be extremely valuable and one that motivates many algorithms that we have in geometry and shape analysis. In particular, let's say I have a big data set of a bunch of 3D shapes in the world out there. They're all expressed as triangle meshes or point clouds or what have you. And now, for each of my shapes, I now have a new shape, like a query. And I want to answer the question, like, what shapes in my database are the closest to my query shape? This is a reasonable question to ask. We do this with data all the time. There's a problem, which is shapes are not vectors. We can't like compute distances between them easily, right? So one thing that you can do is take all the shapes in your database, hit each of them with your drumstick, and write down a list of frequencies that they react. And that thing is now a vector that describes your shape. And you can retrieve new shapes by looking at distances between those vectors. This is a technique that goes back to the 90s. It's called shape DNA, which is a very dated 90s kind of thing to call your research paper. And essentially, this was one of the dominant methods for shape retrieval for decades. It was essentially exactly this, just like kind of a computational version of that mathematical story that people had studied for many years. And it turns out that in real life, it's very hard to encounter shapes that are isospectral. So this is a pretty effective technique. Now, moving forward, a lot of these are kind of low-dimensional things. When we talk about data and some applications outside of computer graphics, we're going to have to invoke some fancier theories of geometry, including Riemannian geometry. Now, Riemann had an absolutely brilliant observation about the world, which is totally obvious in retrospect. So here's a map of the globe. And let's say that I want to compute the distance between, what is this, like, Mexico and Africa, somewhere, down in the middle, and then somewhere up north here, I guess in Russia somewhere. How do I do that? Well, do I just like hold up my yardstick to the screen here, and it's like, what, about 2 feet? And I say, OK, great. So it's like 2 feet from Mexico to wherever that is in Africa. No, obviously, this is a stand-in for the geometry of the actual globe, which it turns out is much bigger than this screen. Yeah? Moreover, things get a little complicated because is the way that I compute geodesics or shortest paths in the parallel in the middle here going to be the same as the way that I compute shortest paths at the top? You're shaking your head. Why not?
Because the Earth is curved and this is just a projection onto the flat surface.
That's exactly right. The Earth is curved, and this board isn't. It's one of many frustrating things about the projector in this classroom. And because of that, essentially what Riemann said is that we have to kind of separate out our notion of topology and connectivity from our notion of shape. Right? So like the shape of the board, or the screen here, is not going to be the shape we care about. But at the same time, this map does tell us something. It tells us like what points are connected to what, where the ocean is, and so on. So how did Riemann get around that? Well, Riemann decided to think a lot about dot products. Right? So in other words, let's say that I want to measure lengths and angles. Right? But when I measure lengths and angles, I want to measure them like they'd be on the actual Earth, not on this screen. Well, what Riemann does is he introduces an object, right? This is the Riemannian metric, which is like a little matrix that sits at every point on the plane here and just tells me how to take a dot product, right? So it says like, you know, my yardstick down here is 1 inch, my yardstick up there is 2 inches. And that is a function of where I am on this two-dimensional plane. Does that kind of high-level picture make sense? And so essentially, in Riemannian geometry, we divorce connectivity from embedding, right? Like this is not embedded. I have not like drawn a sphere for you here. But I can still sense notions like curvature just by looking at how that dot product changes as I walk along the domain, right? And so that turns out to be an extremely valuable theory and is actually more than sufficient for doing a lot of geometric calculation. That it turns out not all geometry is embedded, at least when it's handed to you. And you can still do a lot of the same math that we'll do in the first part of this class, just having access to a dot product function, like not actually having access to coordinates. This is like kind of a new way to think about shape. Or another picture here is like, what would geometry, feel like to an ant crawling along the surface, right? As everybody knows, the only thing ants can do is compute dot products, and only on their toes, right? They have no idea what it means to compute a dot product over there, right? And so, as they walk around the surface, these things can change. They can make little local measurements. And then Riemannian geometry is all about how you take those local measurements and assemble them into a global picture of the universe around you. Okay, and then finally, we'll touch upon some other very modern ideas in geometry. One really fun one that I always intend to cover in this class, and then we run out of time, involves putting geometry on geometry. This is a really fun area to think about and a little bit abstract. But for instance, let's say that I have a surface, and I look at all the different ways to bend it. Right? So people do this a lot in medical image analysis. Right? So like I go out into the world and I scan everybody's livers. It's been on my to-do list for a long time. And when I do that, livers are like weird, glorpy objects, and they can vary in all kinds of weird ways. Right? There's no obvious low-dimensional axis there. But there's still some kind of manifold structure, like some shapes are more similar than others. And so there's a notion of infinite dimensional geometry out there. Well, people try to actually take these finite dimensional things that we'll talk about a lot in this course and lift them to the infinite dimensional spaces, like the set of all possible surfaces. And this isn't just abstract. They use it for things like, medical image analysis, like what does it mean to do principal component analysis on a set of livers? Or in computer animation, like maybe I want to compute the shortest path between two poses of a surface because I'm going to use that for animating from one to the next. But there's no obvious geometry on that space, right? I need to figure out what that means and make sure that it's well posed. And then finally, maybe at the end of this class, we'll cover one or two other kind of fun things. In physics, of course, you end up with a lot of really strange abstract notions of geometry. For instance, in computer graphics, it's very popular to think about geometric mechanics problems where you take your physical simulation and you map it into some other domain where it makes more sense. So think about this double pendulum here. So like I've got two sticks that are tied together and kind of hanging off a hinge on the ceiling here. Naturally, the geometry where this physics problem lies probably isn't on like the plane, it's on a torus, right? Because there's kind of two angles to work with, right? And taking like Newton's laws and translating them into this curved space now can provide you both with a lot of kind of high-level benefit in terms of mathematical analysis of the physical system, and also suggests some really modern ways to do numerical simulation, right? So a lot of times people put a lot of effort in computer graphics and simulation domains into figuring out like, what are the real degrees of freedom sitting underneath a physical problem, and then how can I leverage those to make a higher quality simulation? And then finally, probably the weakest notions of geometry we have out there are more just based on distances and probabilities and uncertainty, right? These days we all work with data, which is messy and has noise and all that kind of thing. And maybe we don't even have notions of curvature and derivative. We just have like discrete samples of some object that's like sitting in space. And then all we can do are very coarse measurements, like approximate distances between faraway things, right? And then the questions become very different, like what kind of geometry can I do if I only have really far away samples that's missing a lot of information? Or in areas like optimal transport, how can I do geometry when all I have is like a fuzzy notion of the shape that I have access to, right? All I have is like probability of like, I think there's something over here. Can I still compute distances? Possibly. And then at the coarsest level is the area of topology, which is not geometry at all, which just has to do with connectivity, right? How things are glued together. So there's a whole toolbox out there. We probably will not cover it in this course, involving how you can sense connectivity and persistence through just very coarse measurements on a domain when you're missing a lot of information. But there's some really fun course project directions and additional reading you guys can do in this particular domain. I think MIT doesn't have too many experts in this particular space, which is too bad. It's a fun research field. Have I scared you yet? There's a lot of cool math to be learned in this class. These are fun stuff. Okay, so in geometry, at least in applied geometry, we have the pleasure of having kind of one foot in theory and one foot in computation, and both of our feet are on very unstable ground. And so I've told you a little bit about the kind of theoretical ideas that we'll be drawing from. Now let me tell you a little bit about the computational toolbox and what it will take to translate that theory into actual algorithms that we can apply in our favorite settings. Now, unfortunately for us, as generalists in geometry, it's going to be really tough to come up with one algorithm or one model that applies to everybody's favorite application. The reality is that in computational universe, we encounter shapes in all kinds of different forms, right? So for example, in the computer graphics universe, we tend to see shapes as like triangulated surfaces or maybe CAD models. In other areas, maybe you have a big cloud of data points and no notion of connectivity between them. In certain corners of CS theory, for example, your only notion of shape is like, it's not even a list of points. It's just, I have 10 points and here's a matrix of distances between them, and that's all I have. Each of these is a different way to give you some notion of shape to your computer, but obviously translating this into an algorithm that makes use of these mathematical theories is going to require a lot of domain expertise in whatever area you care about. And so even though our notions of shapes with basically any object that has some idea of like distances or curvature, coming up with like the one generic geometry toolbox to rule them all would be a very ambitious task indeed. And let's talk a tiny bit about why this is so hard. So I'm going to give you the easiest possible case of thinking about geometry in some sense, which is this dolphin here. I believe this is what comes up if you go on Wikipedia for triangle mesh. And it's a nice one. In particular here, we have this nice dolphin shape. I think from where you guys are all sitting, which is a little bit of a distance, it kind of looks like a smooth surface, right? It looks like a sea creature of some sort, right? Now, if we think about it a little more and we start to become pedantic mathematicians, the story gets a little more complicated than that, right? Like, we're used to thinking of dolphins as like cute, smooth sea creatures, but this dolphin is not smooth at all, right? This is piecewise flat. Right? There's a bunch of little flat triangle facets on this surface that are connected in very sharp edges. Yeah? So these notions of curvature that I was talking about before, like computing derivatives and so on, what are they going to mean on a surface like this? Like, can I just take my favorite formula from differential geometry and put it here and expect it to work? You're shaking your head, and you're absolutely right. Like, what is this curvature? Well, it's like 0 here, 0 there, it's infinity here. Right? And so essentially taking that theory and translating it to the discrete case is going to require some very careful work, right? Like some interpretation, discretization, whatever you want to call it, in order to make geometry make sense on this domain. And so we're going to do a kind of funny thing a lot in this class, which is we'll have kind of one foot in the smooth universe and be trying to make all the smooth stuff work on these fundamentally non-smooth objects. On the other hand, we're going to have one foot on the discrete side and say, like, well, our algorithms at the end of the day are iterating over a list of triangles. So how can we come up with like differential geometry inspired techniques that still make sense on a piecewise flat domain? right? And these kinds of questions are totally bizarre, and they lead to total contradictions in terms. Like, for example, we'll talk a lot about a research field called discrete differential geometry, which mathematicians hate the name of because discrete and differential are two things that just like shouldn't be next to each other. Yeah? We'll see that it makes sense, but only in a certain coarse way, right? So for example, here, as I've already mentioned, a reasonable question you might ask is like, what does it mean for a triangle mesh to have curvature? Right? Like what, and if you think about it, this is a kind of a deep question. It's hard to think about, right? There's no notion of like smooth bending that's happening on these objects. The only thing we have are the lengths of the edges and like the facet angles to work with. We'll see that we can come up with some reasonable notions, but it's going to require you to be kind of a jack of all trades, right? On the one hand, you're going to step back 10 feet from your surfaces and kind of view them as approximations of smooth objects, but at the same time, you're going to take a little microscope to them and have to deal with all these little faceted pieces. Right, so we're going to spend a lot of time in this course developing this idea of discrete differential geometry, what it means to take derivatives on a surface that has no derivatives. And obviously what that means is we're going to have to build up a theory of geometry from the ground up that works on this much coarser set of domains. This is a popular field to study. There are many different themes. The basic one that I like to think about is discrete versus discretized geometry. How many of us have seen this goofy set of terminology before? Oh, good. Finally, I lost you. Fantastic. How many of us have taken like a numerical methods class of some sort, or like approximated a derivative on a computer or something? You know, take f of t plus h minus f of t divided by h. If I do that, am I computing a derivative? No, right? I'm computing an approximate derivative. And the kinds of theory that I tend to derive are things like, as h goes to 0, my approximate derivative gives me the true derivative of a function, right? In fact, this coming fall, I'll be teaching undergrad numerical analysis, and we're going to do a lot of that. But what's the difference between that and like that dolphin mesh that I showed you before? Can I do those kinds of limits? Like if I'm unsatisfied with my derivative, can I refine? The answer is no, right? Like all I have at my disposal is that mesh, right? I have to decide what happens in between those vertices. Right? So somehow that theory, that limiting idea that I want to take h to 0 and like measure approximation quality, that discretized picture of the universe, sometimes it just doesn't make sense. My data is at some resolution and I have nothing more to work with. And so in discrete differential geometry, they pursue kind of an alternative picture of the universe where they say, I'm going to define a new object that I will call my discrete derivative. Like maybe for h equal to 5, I'll look at f of t plus h minus f of t divided by h. And that object has its own properties and things that I can study. And what people in discrete differential geometry try to do, which is kind of cool, is derive an entire discrete theory that parallels the smooth ones. So for example, we're going to be able to derive formulas that look an awful lot like integration by parts, but now are kind of like summations over triangles rather than integrals, right? And these are the kinds of things that we'll do a lot of. In fact, starting in our next lecture, we're going to talk about curvature of a plane curve, and we'll see that we can make a nice version of what it means for a curve to bend around in the plane. So in this funny research field that we're going to spend a lot of time talking about, right, the idea is to come up with this nice discrete theory that really makes sense on meshed objects and things that are composed of individual facets and segments. The big theme that we're going to be pursuing a lot is going to be something called structure preservation. And this is going to be kind of a meme that runs throughout this course. The idea is that essentially, we're going to take our favorite theorem from the smooth theory, you know, something that's true about curvature. So for example, the Gauss-Bonnet theorem is a famous one. If I take a certain notion of curvature, like some notion of bendiness on a surface, and I integrate it over the whole surface, I get a constant. Has to do with the topology. And we're going to say, can I come up with a notion of curvature and a notion of integration, by the way, so that I have a discrete Gauss-Bonnet theorem. So like when I take the integral of my discrete curvature, I get that same constant. Notice in the discretized universe, that would not be true, right? I would prove a different thing, which says that like I have some notion of curvature that's not totally accurate. I have some notion of integral, which is an approximation. I put them together and I get a number that's close to the one that I wanted. Right? In discrete differential geometry, we want there to be an equal sign. Yeah? So a nice example of that is going to be what we cover in detail in our next lecture, which has to do with turning numbers. Yeah, I see. Okay, let me finish this sentence. Which is going to relate to the winding number theorem for curves in the plane. So essentially, there's a constant associated to a curve in the plane, which is like the number of times that it turns around itself. You can see what that looks like here. And we can come up with a similar constant for like a polygon, right? And one way to get that constant is by integrating the curvature of the curve. Like if you have the right notion of bendiness and you integrate it around the loop, you'll get the winding number. Turns out that makes sense. Now down here, we're going to apply a theory you might remember from high school geometry. You remember this one where you add up the exterior angles in a polygon and you get 2 pi? Well, wait a second. There's a constant that's sitting inside of a calculation that looks kind of like curvature. So we're going to leverage that observation to come up with a discrete theory of curvature that matches the smooth one with an equal sign. Your question?
This answers my question.
Fantastic. Any other questions? 1, 2, 3, 4, 5. Okay, fantastic. So that's going to be the overall kind of aesthetic. Notice there's one thing I haven't justified here, right? I could cook up this weird notion of curvature easily enough. You can kind of see it from this picture if you stare at it long enough. I haven't actually told you that these two notions of curvature have anything to do with each other, right? All I've shown is there's some structure that's preserved. A different question I could answer is like, is this actually a good approximation of smooth curvature? That's the sort of other side of the same coin, the discretized picture of the universe. And then I can ask about convergence, right? So in other words, I have, for example, a curve in the plane, and I approximate it with a bunch of line segments, right? And I have some notion of discrete curvature that sits maybe at the vertices of this object. I could ask the question, like, if I take that approximation, I refine it, I start, taking more and more samples from my curve, does my curvature calculation actually converge to the thing of the smooth object? It's not going to be the same as structure preservation. Leticia, did you have a question? I saw your hand for a second. Okay, no problem. Okay, so we have two different ideas. Yes?
If we retain some of the topological invariants, like the discrete version of Gauss-Bonnet, is it possible to find things that maintain those invariants but don't converge as you?
Is it possible to, that's a fantastic question. So to phrase it differently, are convergence and structure preservation somehow in conflict of each other, right? Because the reality is we'd love to have it all, right? We want to have like a perfect thing that behaves really nicely in the smooth case, also approximates the, in the limit of refinement, everything converges, life is good. Yeah, that'd be beautiful if I had that theory. I present it to you. Right, so to put it differently, the question is, can we have it all? Can we have convergence, structure preservation, maybe easy algorithms to compute this stuff, everything all in one shot? Yes, exactly the right question. What do we think? Well, in some sense, I'm asking a question, so you probably know the answer. Probably not. Yeah, nope. The answer is no. In fact, fundamentally, convergence and structure preservation are in conflict with one another. And what we're going to find, and this is where the rubber hits the road in the discrete differential geometry universe, is that there's all kinds of properties that we're going to want for our discrete object to be true, and we're going to have to choose some subset of each other because they're going to end up being in conflict with one another. So a nice example of that is this Laplace operator. The Laplace operator has so many properties. We're going to prove so many of them in this class. I'm like excited already. Unfortunately for us, we're going to come up with this big table of Laplace operator properties. It's like positive definite object, similar to like a positive definite matrix. It's local, right? It's built out of derivatives. What are some other Laplace properties? It has a maximum principle. And essentially, unfortunately for us, what's proven in this research paper from Max Wardetsky is that they put down a list of natural properties for the Laplace operator, and they show an important theoretical limitation that discrete Laplacians cannot satisfy all the natural properties at the same time. What does that mean? That means we can't have a perfect Laplace operator. And maybe we have to pick and choose between the properties that we want. In a funny way, as engineers, this gives us some really interesting flexibility because we're going to have like 10 different matrices that all approximate the same smooth object and have different properties that we might want. And we're going to have to figure out which one is best for a given application, right? Do I care about my matrix being positive definite, or do I want it to be sparse? Do I care about, heat diffusion to look right, or do I care about the wave equation? And sadly, even though they're all the same math, the way that we make them work on a computer will be different. And it is one of the really fine points in this area that's quite hard to think about. Yeah, so it's a fantastic question. But the good news is that there's a big toolbox to draw from when we're designing algorithms and models to work with discrete shapes. And there's lots of different structures to preserve and ways that we can do it numerically. One thing that we'll cover a lot of in this course is numerical partial differential equation. So in case you're you haven't brushed up for a while on how to solve differential equations, it turns out that that is one of the important ways that we analyze a 3D surface. So for example, one of the most famous things that you can do to a shape is turn it into this awkward skeleton here. This is called mean curvature flow, which is basically gradient descent on surface area. That's all mean curvature flow is. I say, as if I were one of the mathematicians that studied it for the last 200 years. Of course, making a differential equation like this work on this curved surface is going to be a tricky matter. So for example, in this class, we'll cover certain approaches to finite element method at a very coarse level. If you go to the mechanical engineering department, you'll do quite a bit more of like, how do you take an equation like the heat equation and make it work on an object that's composed of a bunch of points and triangles. Beyond that, another thing that comes up quite a bit in geometry is large-scale optimization. My favorite example of this, which feels benign, is surface parametrization. So here, I've got this cow, and in fact, I was kind enough to take scissors to the cow, so it's secretly a disk, meaning that I can map it into the plane without tearing it, because I already tore it. And the problem with surface parametrization is to find the mapping of this cow into a rug with the lowest amount of distortion. Now, it's not vegan, and in addition to that, there's a larger issue, which is the cow is mostly positively curved, right? It's bent, and the plane is not, and so I'm going to have to incur some distortion when I map it. Incidentally, this is a fundamental operation in computer graphics software, because like typically you store the texture of your surface in like an image, which is flat. So if you think about it, this is a very large-scale optimization problem, right? These meshes typically have on the order of hundreds of thousands of vertices, and I have to place every single one of them in the plane in a way that minimizes distortion. So I have an optimization problem with hundreds of thousands of variables. Moreover, if any two triangles occupy the same piece of the plane, arguably the parametrization is useless, right? Because now if I like texture the cow's knee, then like the cow's shoulder is going to get the same color on it, right? Because they're in the same place. That's no good. So I have like hundreds of thousands of variables in my problem. I've got hundreds of thousands squared constraints in my optimization problem. This is something computer graphics people do every day. So large-scale optimization is going to be a critical piece of the toolkit that we have. In addition to differentiable optimization, oftentimes we also encounter discrete structures we have to work with in this field as well. So for example, we'll talk a little bit about meshing problems, which involves taking a surface like this thing. Anybody know what this surface is called? It's called a fan disk. Apparently this is a part of a car. I don't know. But in any event, the fan disk, one of the things that we like to do to it in scientific computing is quad meshing, which is exactly what you see here, right? It's like covered in these little quadrilateral elements, right? In order to do that in a nice efficient fashion, we're going to have to minimize the distortion of all the quads. We want them to be kind of planar and have flat looking edges. But in addition to that, there's discrete structure, like how many quads do I place along a different part of the surface? And where do I place singularities, like this point here, which is adjacent to 1, 2, 3, 4, 5 quads instead of 4, right? There's not a regular grid there. So unfortunately for us, we have both combinatorial and differentiable problems to think about all in one giant mess of a computational toolbox. Sitting underneath all of this is a lot of linear algebra, so especially when we talk about whether you can hear the shape of a drum. Essentially, in some sense, you can view that entire universe as reducing geometry to an eigenvalue problem. We're going to spend a lot of time kind of justifying that and thinking about how we can leverage the computational linear algebra toolkit to do shape analysis with basically no change, just typing in a very careful matrix. And then finally, these days, we leverage all kinds of interesting areas of algebra as well. It's a very popular thing to do, both in graphics, like this old research paper from our group, as well as in some fields like cryo-electron microscopy, involve looking at different algebraic structures, quotient spaces, and representation theory to understand really abstract domains that show up in certain settings. Okay, so I promised you 3 things in today's lecture. Again, today is all about picture book, and then next time we're going to do calculus. The third piece of our puzzle, now we have some notion of like, what does it mean to do modern geometry mathematically? What does it mean to do modern geometry computationally? The last thing we should mention are all the cool applications. Like, where do we actually use this stuff? And the answer is all over the place. I mean, from my perspective, geometry is like unavoidable. It's just, you walk down the hallway and you're walking into shapes, especially when you're me, because I walk into everything. One of the original domains that really thought about these problems carefully was computer graphics. And indeed, many of you, I recognize a lot of students in this class from my undergrad graphics class and from the graphics group in our PhD program. people in computer animation, people in 3D modeling study geometry a lot for obvious reasons, right? The main object that you're manipulating in all of those application domains really is a shape that's like sitting in 3D. And we need to be able to characterize notions of bending and stretching, as well as these days in modern machine learning, we want to solve problems like, if I have an example of like 100 car parts that I've already 3D modeled, can I use that to inform how I make a 3D model of the next car part? These are tricky machine learning statistical problems as well. Computer vision also worries a lot about geometry. For example, our research group works quite a bit with autonomous driving data, which is a fantastic and really messy source of shape, right? So if you see one of these autonomous vehicles driving down the road, you may see, unless it's a Tesla, you'll see that it has this spinning sensor at the top of the car, right? This LiDAR thing, which is essentially collecting the 3D environment around your car, right? The other pedestrians, the other cars, where the road is, all that good stuff. Going from that to inference about what's actually in front of your car and what do you not want to run into is all about geometry processing and shape analysis. In medical imaging, there are so many important applications of geometry. You can understand a lot of the algorithms that input an MRI of your brain, for example, and output all the folds, try to detect the progress of neurodegenerative disease and so on as shape analysis techniques, right? Because even though your MRI data might be coming in on a grid, the reality is that the interesting object is what's sitting inside of the grid, right? Like it's an interesting shape. And how these shapes evolve over time, how they're curved and so on, is really the critical piece of analysis that we need to study in that domain. Folks in manufacturing and fabrication care about shape a lot. You see in 3D printing, lots of geometry analysis going on, asking questions like, is this object printable? Is it does it satisfy the constraint of a particular manufacturing technology? That's a big one. So for example, in CNC milling, there's only so much curvature you can have on a given surface because of the way that little drill works in that machine. Does an object stand? Will a bridge that I build collapse? And so on. A lot of these things are all functions of a shape. And indeed, related to that area is architecture. So one of the really fun things that I think has evolved in the computer graphics community, which is cool, is they've become really open-minded to these different applications. And actually one of the little fun subgroups that's wandered into that field is in architecture. And there's some architects out there that want to answer, like, how do I make 3D modeling tools that are flexible enough to deal with architects who are annoying to work with? They have all kinds of weird visions in their mind that are not compatible with, like, Newtonian physics. But at the same time, I want to make a 3D modeling tool that presents to the user like the constraints of materials and environment and gravity in a way that's intuitive and has particular kind of application in terms of shape. Beyond that, for shape analysis, we also can study things like paneling, where I want to take a surface and cover it with windows. Which leads to all kinds of really interesting and specialized geometry. So for example, apparently modeling windows, they come in flat material, which makes sense. And it turns out it's relatively easy to bend. It's relatively difficult to stretch. It makes sense. There's a lot of materials out there where this is the case. Like I can heat it up and it'll bend, but if I start pulling it apart, it'll tear, right? And so you might ask the question of like, okay, how does that constrain? Like if I want to make an interesting building, and I want my windows to be cheap to manufacture, that actually constrains the set of shapes that I can generate. And there's all kinds of interesting algorithms out there that try to model in these different, very constrained domains. A lot of people work in shape collections. This is a really fun area and kind of an emerging one that people study in machine learning. So for example, again, if I go out and I take 1 million brain scans and I want to figure out like which ones are the abnormal ones or something like that, it's probably not the best example. Doing that kind of analysis, it's tricky because these are not data points. They're like objects that are bigger or smaller. They're composed of different numbers of triangles and so on. Or maybe I look at this collection of teddy bears and I want to know which ones have their arms up. Why, you might ask? I don't know. These kinds of analytical problems are tricky because now we're coupling together these notions of geometry with very large data sets, and efficiency becomes really critical. Related to these problems is correspondence, where like I'm given 2 different geometric domains. I want to come up with a map from one end to the other. So for example, in this area, maybe I put a lot of time putting a cute texture on this cat. Now I make a new model of a new cat. Can I transfer that information over? Now if you go into machine learning and you look at transfer learning and the kind of machinery that people use there, you'll see that the algorithms are actually quite similar. That in transfer learning, like for example, I go into Walmart and I label all the product images. And now I go into some other store and I take a photo of a product. there's a lot of shared structure, right? This is the same product, but like maybe the shelves look a little different. Can I transfer my learned model from one domain into the other is going to end up being basically a mapping problem. We'll see that essentially the machinery, at least as of 10, 20 years ago, for solving both of these things is quite similar mathematically. People also work on deformation transfer. So like, you know, if my colleague Sofiane is moving his face around and now I have these animated characters, what does it mean to kind of guide one by moving the other? People in computational physics use geometry tools quite a bit. So for example, there's a really fun research paper a couple of years ago that studies the path that honey takes when you pour it on a treadmill. I love this research paper. You guys, anybody know what this is called? I don't know why you would. This is called a viscous thread. I will give you like a vanishing amount of extra credit if you manage to reproduce the experiments in this paper, which especially double the amount of extra credit if you do it in the Z Center. Essentially, if you take a viscous fluid like honey and you take a treadmill, like one of these running devices, they're good for nothing, but maybe for this experiment, and now you pour your honey on the treadmill, you can get all kinds of really interesting shapes. So for example, if your treadmill is going really, really fast, obviously the honey's going to get pulled out and you just get a straight line. But then eventually, if your treadmill is moving really slowly, it starts to curl on itself, right? And there's all these physical phenomena that can happen, like waves and loops and so on, that have to do with the relationship between the thickness of the honey and the velocity of your treadmill. And in fact, there's an entire little branch of geometry research dedicated to characterizing this system mathematically and then faithfully reproducing it numerically. And it's really fun to look at these research papers. They seem to struggle to find application, but there are fun animations of people like pouring chocolate on a sundae and having it curl in just the right way. But also people do this in all kinds of other branches as well. There's scientific visualization is another nice application of these geometry tools. In fact, when we talk about spectral geometry, we'll see that this is the same machinery people use to understand certain like molecular systems and their main modes of vibration. We look at segmentation, finding interesting folds in your brain. And we'll also talk about some high-level just data analysis applications as well. So in fact, when we present the Laplace operator, we're going to do the Laplace operator on meshes, graphs, and point clouds all at the same time. And these have different applications in different domains. So these days, if you are in graph-based machine learning and you're studying GNNs, then essentially all the dominant theory and the way that people talk about these objects is through exactly the same operator that we'll use to study that can you hear the shape of a drum problem. And I think that also is going to provide us with some clues as to good ways to engineer graph neural networks in a way that makes sense. Like the theory is the same, and there's some interesting research problems that are hiding there that I think can be borrowed from this domain. And finally, we'll also talk about some statistical problems as well. So for example, here are two famous kind of model data sets, which are sort of intrinsically like two-dimensional in this case, like this S shape or this Swiss roll. And we'll discuss different statistical methods for kind of identifying that low-dimensional structure. So here, principal component analysis won't cut it, right? Like there's no plane I can project these shapes on that'll give me the structure that I expect to see, right? So we'll talk about some methods for doing that as well. Okay, so as promised, we'll end a tiny bit early. That's it for today. My goal is basically to get you guys excited about all the cool things that we'll talk about in this course. In our next lecture, we're going to talk about geometry of curves as a kind of a motivator for how to compute curvature, integrals, integration by parts, first variations, all that kind of stuff. And that'll all be coming in our next lecture. Stay tuned in your email. I'm going to try and get a different classroom because this one is not practical for board writing. But we will see whether I can do that or not. So with that, I will see you all on Thursday. See if I can turn off this recording.